Have you ever truly watched a simple cup of coffee as it cools on your kitchen table? It's a quiet, everyday event, one we barely notice. But within that small ceramic vessel, a grand cosmic drama is unfolding. The universe is whispering its most fundamental secrets. Why does the heat seem to vanish into the air? Why doesn't the cool air spontaneously gather its warmth and heat your coffee back up? These questions are gateways to understanding the engine that drives the cosmos. The principles governing that cooling cup are the same ones that orchestrate the birth of stars, the death of stars, the formation of galaxies, the intricate dance of life itself. This is the story of thermodynamics. In our journey today, we will explore this profound science. To begin our story, we must first understand its main character, energy. What is it really? We use the word all the time, having energy, saving energy, using energy. But in physics, energy has a very specific and beautiful meaning. It is the universe's capacity to cause change, to do work. It is the fundamental currency for all transactions in the cosmos. Think of it like this. If you want to move something, change its temperature, or alter its chemical state, you must spend some energy. Energy comes in a dazzling variety of forms. Kinetic energy, energy of motion. A planet orbiting its star, a child running across a field. Potential energy, stored energy. Chemical energy locked in a log spark releasing heat and light. Gravitational potential, a rock teetering on a cliff. Rock falling. Conversion to kinetic energy. All these forms can transform into one another. One of the most relatable forms of energy is heat. Heat is not a substance, not an invisible fluid as scientists once thought. Heat is energy in transit. It is the flow of energy from a hotter object to a colder one, driven by a temperature difference. When you touch a hot stove, you're not feeling hotness itself. You're feeling a massive transfer of energy from vibrating stove atoms to the atoms in your hand. This flow is what we perceive as heat. It's a dynamic river, always flowing from high temperature to low. Understanding this distinction is crucial. Temperature measures average kinetic energy of atoms or molecules, a snapshot of how vigorously particles jiggle. Hot tea, molecules agitated. Cold lemonade, molecules sluggish. Heat is the energy that moves because of that difference. It's the process, not the property. This relationship between temperature and heat is the foundation of thermodynamics. By the end of our exploration, that simple cup of coffee will look different to you. You will see it not just as a beverage losing its warmth. Before we get to the first law, there's a lesser-known but equally profound rule. They called it the Zeroth law, a prequel to the others. It might sound blindingly obvious at first, but its implication is what makes measurement of the universe possible. The Zeroth law is all about thermal equilibrium, the state where things have settled and stopped exchanging heat. It states that if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A must also be in thermal equilibrium with object C. It's a simple rule of transitive property applied to the world of heat. Think about it with a simple, everyday example. Imagine you have a cup of hot tea, object A. You place a metal spoon, object B, into it. After a few moments, the spoon becomes hot. The tea and the spoon have reached thermal equilibrium. They are at the same temperature. Now, you take a thermometer, object C, and place it in the tea. You wait until the reading stops changing. The thermometer is now in equilibrium with the tea. The Zeroth law guarantees that if you now measure the spoon, you get the exact same reading. This law is the silent hero behind every thermometer ever made. When you place a thermometer under your tongue to see if you have a fever, you are invoking the Zeroth law. Your body and the thermometer exchange heat until they reach the same temperature, thermal equilibrium. The thermometer isn't measuring some abstract property. It is simply reporting its own temperature, which, thanks to this law, is also your body's temperature. Without this fundamental principle of balance, we would have no reliable way to compare temperatures. The concept of temperature itself would be meaningless. So, the Zeroth law establishes temperature as a fundamental, measurable property of the universe. If two objects have the same temperature, no net heat will flow. They are in a state of balance. Now we come to the first law of thermodynamics, one of the most powerful and absolute conservation laws in all of science. It is often called the law of conservation of energy. Energy cannot be created or destroyed. It can only be converted from one form to another. The total amount of energy in an isolated system, and in the universe as a whole, is constant. It is a strict cosmic budget. Consider the act of burning a log in a fireplace. It might seem as though you are destroying the log and creating heat and light. But the first law tells us a different story. The log contains chemical potential energy in its molecular bonds. A flame supplies activation energy to break those bonds. The chemical energy is released, transforming into thermal energy, heat, electromagnetic energy, light. The total energy of the initial log and the oxygen it consumed equals the total energy of ash, smoke, heat, and light. Not a single joule is lost. This law is at work all around you and inside you. When you eat an apple, your body doesn't create energy from nothing. It metabolizes sugars, breaking chemical bonds to release stored energy. That energy becomes the kinetic energy of your moving muscles, the electrical energy of your firing neurons. Thermal energy maintains your body at 37 degrees Celsius. Every action, every thought, is an energy conversion, perfectly balanced according to the first law. If the first law tells us that energy is conserved, the second law of thermodynamics tells us about the direction of its flow. It introduces us to the universe's preference for messiness. One simple statement is this: heat naturally flows from a hotter object to a colder object, never spontaneously in the reverse direction. Your coffee cools because its heat spreads into the cooler room. The room doesn't get colder to heat your coffee. This one-way street for heat gives time its arrow. It introduces one of the most fascinating concepts: entropy. Entropy is a measure of disorder, or the dispersal of energy. In any isolated system, total entropy tends to increase over time. Energy spreads out, becomes less concentrated, and more evenly distributed. A pristine ice sculpture, a highly ordered state, inevitably melts into a puddle in a warm room. Energy from the room spreads into the ice, increasing overall entropy. A brand new deck, perfectly ordered, low entropy. Shuffle it, and it becomes a high entropy state. It's astronomically improbable to spontaneously return to perfect order. Since the Big Bang, energy has been spreading and disorder increasing. Entropy's rise fixes the direction of events. Eggs break but don't unbreak. Smoke disperses but doesn't regather. No engine can be perfectly efficient. Some energy becomes unavoidable waste heat, warming the engine and air. This isn't bad design. It's a mandatory entropy tax. This tribute to entropy sets the ultimate limit on useful work. Section 6. Absolute zero, the ultimate stillness of the third law. We now visit the coldest frontier imaginable: absolute zero. This brings us to the third law of thermodynamics. It describes matter as it approaches this ultimate limit of cold. As the temperature of a perfect crystal approaches 273.15 degrees, 0 Kelvin, its entropy approaches a constant minimum. The frantic dance slows. Atoms reach their lowest possible energy, perfect order. It is impossible to reach absolute zero in a finite number of steps. Each cooling step gets exponentially harder. The finish line moves as you approach. Scientists reach billionths of a degree above absolute zero, creating exotic states like Bose-Einstein condensates, but never the final destination. The third law sets the universe's cold boundary. It provides a baseline for entropy, letting scientists compute absolute entropy, vital for predicting reactions and material properties. It completes our picture with the baseline of perfect order. Section 7. Engines of Creation. Thermodynamic laws are blueprints for engines. An engine converts thermal energy into mechanical work. From our sun to your car, they share principles. They harness heat flow from hot to cold, siphoning some to do useful work. This process powers civilization. Heat source boils water, steam expands, pushes a piston, cools and vents to the cold reservoir. First law, work plus waste heat equals heat in. Second law, you must dump waste heat, and without a temperature difference, no work is possible. Efficiency is limited by the difference between hot and cold. That's why engines need radiators and airflow. Hot gas expands, pushes pistons, turns the crank. To reset the cycle, heat must be removed to the cooler air. Waste heat is not a flaw. It's required by the second law. Every engine pays the entropy tax. Section 8. The cold equation. How refrigerators defy the flow. A refrigerator seems to make heat flow from cold to hot. It chills its interior and warms your kitchen. No violation, but it comes at a cost. Work. A fridge is a heat pump that uses work to move heat uphill. Compress, condense outside, release heat to the room. Expand, evaporate inside, absorb heat from food. Repeat. Electrical work pushes heat from cold to hot. Inside, entropy decreases. Local order rises. But the compressor and coils increase entropy more in the room. The universe's books are still balanced. You can make a small pocket of order, but only by creating more disorder elsewhere. A perfect, small-scale demonstration of cosmic law. Energy moving from concentration to diffusion. The very arrow of time. Section 9. Entropy, the unseen architect of our world. We've talked about entropy, this measure of disorder, but it's far more. It shapes our world, our universe, even our lives. Entropy is the reason time flows forward. The universe remembers the past, a state of lower entropy. As the universe expands and cools, it becomes more disordered. Every process is a small step along that one-way journey. Life is an island of breathtakingly complex order, low internal entropy. Like a refrigerator, life maintains order by consuming energy, sunlight and food, and releasing heat and waste to the environment. Pumping entropy out locally, raising it globally. Life is a temporary eddy in a cosmic river toward chaos. When coffee cools or dust settles, you witness the universe spreading energy, increasing entropy, marching forward in time.